Alright, Leon Chiva here and welcome to the workshop. We've all heard these myths, these automotive urban legends whispered from one car enthusiast to another, posted on forums and debated endlessly at car meets. You know the ones: premium gas turns your daily driver into a rocket. Or you gotta baby that new engine for 1,000 miles or else. Some sound plausible, some sound downright ridiculous. But how many of them actually hold up when put to the real hard test? Well, today, that's exactly what we're here to do. We're not just talking about it, we're getting our hands dirty. I've got a lineup of some of the most persistent, most argued about car myths you can imagine. We're talking fuel, engines, performance parts, and even some Hollywood-inspired shenanigans. We're going to isolate the variables, run controlled experiments, gather the data, and see what's fact and what's pure fiction. This isn't about opinion, it's about empirical evidence. So buckle up because things are about to get interesting. We're going to build, we're going to test, we might break a few things, safely of course, and hopefully we're going to bust some myths wide open. Or, hey, maybe we'll confirm a few. That's the beauty of science and experimentation. You never know until you try. Are you ready to dive in and separate the automotive facts from the fiction with me? Let's fire it up! First up on our myth-busting agenda is a classic, one I hear all the time. Putting premium gasoline in car will make it perform better, give you more horsepower, and better fuel economy. It sounds appealing, right? Pay a little extra at the pump, get a sportier, more efficient ride. But is there any actual science behind this? Or is it just clever marketing and wishful thinking playing tricks on our minds and our wallets? That's what we're here to find out, with some good old-fashioned testing. The core of this myth revolves around octane rating. You see those numbers at the pump: 87, 89, 91, 93. Higher octane doesn't mean more energy in the fuel, which is a common misconception. What it actually signifies is the fuel's resistance to pre-ignition, or knocking, pinging. High-performance engines, often with higher compression ratios or turbochargers, generate more heat and pressure in the cylinders. They higher octane fuel to prevent that fuel-air mixture from igniting prematurely, before the spark plug fires, which can damage an engine. So, our big question is, if your car is designed for regular 87 octane, does feeding it the pricier 91 or 93 octane stuff offer any benefit at all? Modern engines are pretty smart. They have knock sensors that can detect pre-ignition. If they sense it, the engine's computer, the ECU, can adjust ignition timing to prevent knocking. This means they can often compensate for slightly lower octane fuel than they might ideally prefer. But does it work the other way around? Can they take of higher octane if they weren't designed for it? To put this to the test, we've got a pretty standard daily driver here, a car whose manufacturer explicitly states that regular 87 octane is perfectly fine. First, we're going to run it on a full tank of 87. We'll do some acceleration tests, 0 to 60 miles per hour, maybe a quarter-mile pass if we can find a safe spot. We'll also do a carefully measured fuel economy loop, trying to maintain consistent speeds and driving conditions to get a baseline MPG reading. We'll listen carefully for any audible engine knock, though with modern cars it's less common to hear it before the sensors pick it up. Then, once that tank is nearly empty, we're going to fill it up with premium, let's say 93 octane. We'll drive it a bit to make sure the new fuel is circulated through the system properly. And then we repeat the exact same tests. Acceleration runs, the same fuel economy loop driven in the same manner. We'll meticulously record all the data. Are the acceleration times any quicker, even by 1/10 of a second? Is the fuel economy measurably better? My hypothesis, based on how engines and octane work, is that for a car not designed or tuned for premium, we're unlikely to see any significant improvement. The engine simply isn't built to take advantage of that higher knock resistance because it doesn't typically operate under conditions where knock would be an issue with the recommended fuel. It's like putting racing slicks on a shopping cart. The potential is there, but the rest of the system can't utilize it. After crunching the numbers from our acceleration runs and our fuel economy loops, we'll lay it all out. We'll compare the data side by side. This is where the truth lies, not in anecdotes, but in cold, hard numbers. Will this car suddenly feel like a sports car? Or will it perform identically just with a lighter wallet? I'm betting on the latter for this specific vehicle, but hey, that's why we test. Let's see what the data tells us. Alright, next up is a topic that causes a lot of anxiety for new car owners, the engine break-in period. The traditional wisdom, passed down through generations of motorists, is that you absolutely baby a new engine for the first 500, 1,000, sometimes even 1,500 miles. This means no hard acceleration, no high RPMs varying your speed, and often an early oil change. The theory is that this gentle treatment allows the piston rings to seat properly against the cylinder walls, bearings to wear in smoothly, and all the fresh metal surfaces to mate perfectly. But here's the thing, manufacturing technology has come a way. We're talking about incredibly precise machining, much tighter tolerances than in the old days, and advanced materials and surface treatments that simply weren't available decades ago. So, the big question is, are these elaborate break-in rituals still necessary for modern engines? Or are they an outdated practice, a relic from a bygone era of looser engineering? This is a really interesting one because it pits tradition against technological advancement. To investigate this, we first need to understand what is supposed to be happening during break-in. The primary concern is usually the piston rings sealing against the cylinder bores. A good seal is crucial for compression, power, and oil control. If the rings don't seat well, you could end up with an engine that burns oil, has less power, and potentially a shorter lifespan. In the past, the surfaces might have been a bit rougher, requiring that gentle wear-in period to smooth things out without causing excessive scoring or damage. So, what do the people who actually the cars say? Well, if you crack open the owner's manual for a new car today, you'll often find much less stringent break-in recommendations than you might expect. Some might suggest avoiding full throttle acceleration or constant high speeds for the first few hundred miles, but the elaborate kid glove rituals are often not mentioned. Some manufacturers even claim their engines are essentially broken in at the factory. This discrepancy between old advice and new manuals is what fuels the debate. For our test, a true comparative long-term wear test on two brand new engines, one babied and one driven normally, would be incredibly time-consuming and expensive. So, we're going to approach this a bit differently. We'll look at what experts, engine builders, automotive engineers are saying now. We can also discuss oil analysis. If there was a significant amount of wear happening, you'd expect to see more metal particles in the oil during those initial oil changes. Modern initial oil fills often have special assembly lubricants designed to aid this very early stage of an engine's life. One aspect we simulate, or at least discuss with data, is the RPM limit. The fear is that high RPMs on a new engine will cause excessive wear or prevent proper ring seating. However, some argue that varied RPMs, including some moderate loads and bursts of acceleration, once the engine is warm of course, are actually for seating rings because it helps apply adequate pressure. Constant low RPMs or lugging the engine might not provide enough pressure for the rings to seal optimally against the cylinder walls. Ultimately, the best advice is likely to follow the manufacturer's specific recommendations for vehicle. They designed and built the engine, they know its tolerances and material properties. If they say drive it normally but avoid extremes for 500 miles, that's probably sound advice. The idea of having to drive like your grandma for a month straight might be more myth than modern reality. We'll gather the evidence from manuals, expert opinions, and the science of modern engine manufacturing to reach a verdict. This next myth taps into a strange kind of brand loyalty you often see with car folks. You should never change the brand of oil you use in your engine, and definitely don't mix different brands, or you'll risk sludge buildup and engine damage. It's almost like a superstition for some. Pick a brand when the car is new, and stick with it for life, or face the dire consequences. But is there any truth to this, or is it just good marketing by oil companies that has us spooked? Let's break down what engine oil actually is. It's primarily composed of base oils, which can be conventional, refined from crude oil, or synthetic, chemically engineered, and an additive package. These additives are crucial. They include detergents to keep the engine clean, dispersants to hold contaminants in suspension, anti-wear agents, viscosity index improvers to help oil flow well at different temperatures, rust and corrosion inhibitors, and more. It's a complex chemical cocktail designed to protect your engine under extreme conditions. The fear behind the "don't switch brands" myth seems to stem from the idea that different brands use incompatible additive packages. The worry is that if you mix them or switch from one to another, these additives might react negatively, perhaps causing them to fall out of solution, reduce their effectiveness, or even create harmful deposits like sludge. This sounds plausible on the surface, but we need to consider industry standards. Most reputable oils on the market, whether conventional or synthetic, have to meet certain minimum performance standards set by organizations like the American Petroleum Institute, API, or the International Lubricant Standardization and Approval Committee, ILSAC. You'll see their certification marks, like the API Starburst or Donut, on the bottle. These standards ensure a baseline level of protection and compatibility. If oils widely available to consumers were known to cause problems when switched, these organizations would likely have addressed it. Now let's talk about conventional versus synthetic oils. Synthetics generally offer better performance, especially at extreme temperatures, both hot and cold, better resistance to breakdown, and often longer change intervals. Can you switch from conventional to synthetic or vice versa? Generally, yes. You can even mix them, that's what synthetic blends are. Though if you mix synthetic with conventional, you'll dilute the benefits of the full synthetic. The key is always to use the correct viscosity grade, like 5W30 or 0W20, recommended by your car's manufacturer. So what about sticking to one brand? While some premium brands might boast about their proprietary additive formulas, the reality is that as long as you're using a quality oil that meets the specifications for your vehicle, check that owner's manual again, switching between reputable brands is highly unlikely to cause any harm. The detergents in modern oils are designed to be robust. If you're changing your oil at the recommended intervals with the correct type of oil, your engine should remain clean and well protected, regardless of which major brand you picked up on sale this week. To visually demonstrate, we can't easily induce sludge by just switching brands in a short-term test. However, we can show examples of engines that suffered from sludge, usually due to severely neglected oil changes, using the wrong type of oil, or persistent overheating, not from brand switching. We can also show the API certification marks and explain what they mean. The real enemy here isn't brand variety, it's neglect and using oil that doesn't meet your engine's needs. So, this myth feels like it's leaning heavily towards busted. This next one pops up in the shadowy corners of the internet from time to time, promising almost too good to be true results. Adding a small amount of acetone, yes, the stuff in nail polish remover, to your car's fuel tank can dramatically improve your mileage. The claims are sometimes wild, suggesting 20%, 30%, even 40% increases in fuel efficiency. If this were true, wouldn't we all be doing it? Or is there a dangerous catch? That's what we're here to investigate. The supposed science behind this myth is often pretty vague. Proponents sometimes claim that acetone helps the gasoline vaporize more completely, or burn more efficiently, somehow extracting more energy from each drop. Acetone is a solvent, and it is flammable, so it's not entirely outlandish to think it might combust in an engine. However, gasoline is already a highly refined fuel engineered for optimal performance in internal combustion engines. The idea that a common solvent could magically enhance it seems a bit far-fetched. Our plan for testing this is straightforward but requires extreme care. Acetone is potent stuff. It's a powerful solvent that can be aggressive towards certain plastics, rubbers, and composite materials commonly found in fuel systems. Think fuel lines, seals, O-rings, fuel pump components, and even parts of fuel injectors. So, before we even think about performance, there's a huge safety and material compatibility concern here. We are definitely not recommending anyone try this at home. For our controlled test, we'll use a designated test vehicle. First, just like our premium fuel test will establish a baseline fuel economy, we'll run the car on a precisely measured amount of regular gasoline over a fixed test loop, driving as consistently as possible. We'll calculate the miles per gallon. Then, with all necessary safety precautions, gloves, eye protection, good ventilation, and away from any ignition sources, we'll prepare a fuel mixture with a very small, precisely measured concentration of acetone, based on the ratios commonly suggested by proponents of this myth. Once the acetone-laced fuel is in the tank, we'll repeat the exact same fuel economy test loop, driving in the same manner. We'll meticulously record the fuel consumed and calculate the new miles per gallon. Will we see that incredible boost in efficiency, or will the numbers be stubbornly similar to our baseline? Or, heaven forbid, will they be worse? We also need to pay close attention to how the engine runs. Any signs of rough idling, hesitation, knocking, or other unusual behavior would be red flags. Beyond just the mileage, I'm genuinely concerned about the potential for damage. Even if by some miracle it did offer a tiny temporary mileage boost, which I highly doubt, what's the long-term cost? If acetone is degrading fuel lines from the inside out, or damaging delicate injector components, any perceived savings would be wiped out many times over by expensive repair bills. This isn't just about whether it works, it's about whether it's safe or incredibly foolish. After our test runs, we'll compare the fuel economy figures. I'll be very surprised if we see any significant improvement. In fact, it's possible that altering the carefully balanced chemistry of gasoline with a solvent like acetone could even reduce efficiency or lead to incomplete combustion. And we'll reiterate the serious warnings about the material compatibility issues. This myth has bad idea written all over it, but for the sake of science and to definitively answer the question, we're running the test. Results coming up. Chapter 5, Cold Air Intakes, Huge Horsepower or Hot Air. The cold air intake or CAI. This is one of the most popular first modifications for many car enthusiasts. The promise is alluring, a relatively inexpensive, easy-to-install bolt-on part that will unleash a significant amount of hidden horsepower and torque, not to mention a sportier engine sound. Manufacturers of CAIs often make bold claims about performance gains. But how much of this is marketing hype, and how much is actual measurable power? That's what we're putting on the dynamometer to find out. The theory behind a cold air intake is sound, at least in principle. Engines make power by burning a mixture of air and fuel. Colder air is denser than warmer air. Denser air means more oxygen molecules packed into the same volume. More oxygen, properly mixed with fuel, can lead to a more powerful combustion event. So, the goal of a CAI is to draw cooler air from outside the hot engine bay, instead of the warmer air that a stock intake system might suck in from under the hood. Many aftermarket CAIs achieve this by using an open-element air filter, often conical in shape, relocated to a position presumed to get cooler air, perhaps down in a fender well or behind a headlight, sometimes shielded by a heat barrier. They also often feature smoother, wider diameter intake tubing, which is claimed to reduce restriction and improve airflow compared to the stock plumbing, which might have resonators or convoluted paths designed to reduce intake noise. So, the potential benefits are twofold: cooler air, denser charge, and less restrictive airflow. Sounds great, right? But the question is, how much of a real-world difference does it make, especially on an otherwise stock engine? Are we talking about 1 or 2 horsepower, which might be lost in the noise of dyno variants? Or are we talking about the 10, 15, or even 20 horsepower gains that some manufacturers claim? This is where the chassis dynamometer becomes our best friend, our ultimate arbiter of truth. Our test procedure will be rigorous. We'll take a completely stock car and perform several baseline dyno runs. This gives us a consistent measure of the power and torque the engine is making at the wheels with its factory intake system. We'll record horsepower and torque curves throughout the RPM range. We'll also monitor intake air temperatures using sensors to see just how warm the air is with the stock setup under these conditions. Then, we'll carefully install a popular, reputable aftermarket cold air intake system designed specifically for this vehicle. We'll follow the manufacturer's instructions to the letter. Once it's installed, the car goes right back on the same dyno, ideally on the same day, under similar ambient temperature and humidity conditions to minimize variables. We'll then perform several more dyno runs, again recording horsepower, torque, and intake air temperatures. The moment of truth comes when we overlay the dynograph's stock versus CAI. Where are the gains, if any? Are they across the entire RPM range or only at high RPMs? Is it a peak horsepower gain or more of a filling in of the torque curve in the mid-range? And crucially, what about those intake air temperatures? Did the CAI actually succeed in drawing significantly cooler air during the dyno pulls? Sometimes, an open filter in the engine bay, even with a heat shield, can end up sucking in hotter air when the car is stationary on a dyno, negating the cold air benefit. We'll analyze the data, look at the percentage gains, and discuss whether the cost and effort of installing the CAI translate into a genuinely noticeable performance improvement, or if it's more about the enhanced induction sound, which admittedly many people enjoy, and that's a valid reason to install one too. But for pure, unadulterated power, the dyno doesn't lie. Let's see if this myth of huge HP gains holds water, or if it's just a trickle. Chapter 6. ATF Engine Flush, Secret Cleaner or Mechanical Menace. Here's an old-school mechanics trick that you still hear whispered about, often as a budget way to clean out a sludgy engine. Just before your next oil change, pour a quart of automatic transmission fluid, ATF, into your engine crankcase. Let it idle for 20 to 30 minutes, then drain it out with the old oil. It'll clean out all the gunk. The logic seems to be that ATF is high in detergents and has good solvent properties, so it should dissolve and loosen engine sludge and deposits. Now, on the surface, this has a certain appeal. ATF is a sophisticated fluid designed to operate under high temperatures and pressures in a transmission, and it certainly contains detergents to keep transmission components clean. So the idea that those detergents could work their magic on engine sludge isn't entirely without some basis. However, an engine and a transmission are very different environments with different lubrication needs and different materials. This is where things get a bit dicey. The big concern here is whether ATF is truly compatible with your engine's internal components and its existing motor oil chemistry even for a short period. Motor oil is specifically formulated with additives that protect against wear under the extreme pressures of combustion, manage combustion byproducts, like soot and acids, and maintain viscosity across a wide range of engine operating temperatures. ATF has a different additive package and a different viscosity profile, typically much thinner than most engine oils. Introducing a significant amount of ATF a quart is about 20 to 25% of the oil capacity in many passenger car engines, could drastically alter the properties of the engine oil. It could thin it out too much, reducing its film strength and potentially leading to increased wear on bearings, camshafts, and cylinder walls, especially if the engine is put under any load beyond a gentle idle. There's also the question of seal compatibility. Are the seals in your engine designed to withstand prolonged exposure to ATF chemistry? Probably not. So, for our test, we're not going to risk a perfectly good engine. Instead, we might try to find an older, perhaps already sludged engine that we can partially disassemble, or use a clear valve cover if we can rig one up, to visually assess any cleaning action. A more practical approach for this segment is to consult with lubrication engineers and experienced engine builders. What's their take on this practice? Many modern engine flushes are specifically formulated for this purpose and are likely much safer because they are designed to be compatible with engine oil and internal components for a short cleaning cycle. We could also discuss the why. If an engine is sludged up, it's usually a sign of severe neglect, typically not changing the oil frequently enough, using the wrong type of oil, or persistent overheating issues. A quick fix like an ATF flush, even if it did remove some loose sludge, isn't addressing the root cause and might even dislodge large chunks of debris that could then clog oil passages or the oil pump pickup screen, leading to oil starvation and catastrophic engine failure. That's a serious risk. The safer, recommended way to deal with a sludged engine is often a series of frequent oil changes with a quality motor oil and filter. Perhaps using a reputable, purpose-made engine flush product designed for the job, following its instructions carefully. Or in severe cases, mechanical cleaning, which involves disassembling parts of the engine. So, while the ATF trick might have some anecdotal support from the past, in the context of modern engines and the availability of better, safer products, it feels like a risky proposition. We'll weigh the potential and likely minimal benefits against the very real potential for harm. Chapter 7. The banana in the tailpipe Hollywood stunt or engine stopper. Alright, for our final myth, we're diving headfirst into Hollywood legend, thanks to a certain Axel Foley in Beverly Hills Cop. The classic scene, Eddie Murphy's character stealthily shoves a couple of bananas up the tailpipe of the detective's car, causing it to stall and backfire hilariously when they try to follow him. It's a brilliant comedic moment, but the question we're asking today is, does it actually work? Can a humble banana, or a few of them, really disable a car by blocking its exhaust? The theory is pretty straightforward. An internal combustion engine is essentially an air pump. It sucks in air and fuel combusts it, and then has to expel the exhaust gases out the tailpipe. If you completely block that exit, the engine can't get rid of the spent gases. This creates back pressure, preventing fresh air and fuel from entering the cylinders efficiently, and eventually, the engine should choke and stall. It's like trying to exhale when someone's holding your mouth and nose shut. So, our mission, should we choose to accept it, and we do, is to recreate this scenario. We've got a car, one we don't mind getting a bit fruity, and a bunch of bananas. Safety first, of course. We'll make sure the area is well ventilated as we'll be running an engine, and we'll be careful around the hot exhaust. We're not just going to test one banana, we're going to see what it takes. How many bananas? How firmly do they need to be wedged in there? First, we'll start the car and let it idle normally, just to establish that it's running fine. Then, with the engine off for safety while we're working at the tailpipe, we'll begin the banana insertion process. One banana might just get pulverized or blown out by the exhaust pressure once the engine starts. I suspect it might take a bit more dedication to create a truly effective seal. We'll try to pack them in there good and tight. What happens if the car has dual exhaust pipes? We'd need to block both, presumably. Once we think we have a good banana-based blockage, it's time for the moment of truth. We'll get in, turn the key, and see what happens. Will the engine start at all? If it does start, will it run rough, sputter, backfire, and then stall dramatically as seen in the movies? Or will the exhaust pressure simply build up and eject our fruity obstruction with a comical thwump and a cloud of banana bits? I'm genuinely curious about the physics of this. We also need to consider the state of the banana. A firm, unripe banana might create a better seal than a soft, mushy one. We might even try different techniques, mashing them in, or trying to keep them relatively whole. This is the kind of rigorous scientific inquiry we live for here. It sounds silly, and it is, but there's real physics at play. The pressure an engine can generate in its exhaust system is not insignificant. So, we'll document the process, the number of bananas used, the method of insertion, and the engine's reaction. Will it be a Hollywood-style engine kill, or will the car simply laugh off our potassium-rich assault? This is pure, unadulterated, practical myth-busting at its most fun. Will this iconic movie trope be confirmed, plausible, or busted wide open? Let's get to stuffing some tailpipes, for science, of course. Chapter 8. The Wrench Report, Myths Nailed and Tailed. Well, there you have it. We've put a serious lineup of automotive myths through the ringer, and the results have been fascinating. So, which ones bit the dust, and which ones had a surprising kernel of truth? The premium gas for any car myth? Largely busted for vehicles not requiring it. Modern engine break-in rituals? Mostly busted, but always follow your manufacturer's guidance. Switching oil brands causing harm? Busted, as long as you use the right spec oil. Acetone for better mileage? Absolutely busted and potentially harmful. Cold air intakes giving huge horsepower gains? We'll call that plausible for small gains, but huge is often an overstatement. The dyno showed us the real numbers. Using ATF to clean your engine? Busted as a safe or recommended practice? The risks likely outweigh any unproven benefits. And finally, the banana in the tailpipe? Well, depending on the car and how many bananas you can cram in there, we found it surprisingly plausible that you can cause some serious running issues, maybe even a stall. Hollywood wasn't entirely off base with that one, though it might take more than a couple of casual bananas. It's been an absolute blast testing these out, getting to the bottom of what's real and what's just garage gossip. But the world of car myths is vast and ever-evolving. That's where you come in. Got a myth you want us to test? Something you've always wondered about? Something that sounds too good or too weird to be true? Drop it in the comments below. We're always looking for our next myth-busting challenge. Until then, keep questioning, keep experimenting safely, and I'll see you in the next video.